Hey, let's talk about parallel and perpendicular lines, shall we? Theorem 3.8. Now remember, all these theorems need to be going on like a few pages that you set aside for theorems. You want to have a nice list of all your theorems so that you can use them when you're making neato proofs. So theorem 3.8 says that if two lines are parallel to the same line, then they're parallel to each other. So if A is parallel to B and B is parallel to C, then A is parallel to C. It's kind of like the transitive property for parallel lines. Theorem 3.9. In a plane, now this one, notice you have to say in a plane because lines that don't intersect that are not in a plane can be skew. So we have to make sure we're talking about in a plane. If two lines are perpendicular to the same line, then they're parallel to each other. So if M is perpendicular to T and N is perpendicular to T, why then M is parallel to N. Okay, let's prove this theorem, shall we? Okay, so we are given that in a plane, R is parallel to T and S is parallel to T. We want to prove that R is parallel to S. Alright, well, what can we do? Well, we know that angles 1 and 2 are right angles by the definition of perpendicular. Perpendicular means that they are 90 degrees. So angle 1 is congruent to angle 2. And since corresponding angles are congruent, we got two lines cut by a transversal. Corresponding angles are congruent. Therefore, R and S are congruent. Bada boom, bada bing. Easy proof. Alright, so let's solve a problem. A carpenter plans to install molding on the sides and top of a doorway. The carpenter cuts the ends of the top piece and one end of each side, so the ends of the top piece and one end of each side, at 45-degree angles, as shown. Will the side pieces of the molding be parallel? So, is this going to be parallel to this? That's a good question. We know that the angles at the connecting ends are 45 degrees. We need to determine whether these side pieces are parallel. So let's visualize fitting them together to form new angles. So if I was to stick these two together, I would get 45 plus 45 is 90 degrees. That's the angle addition postulate. And if I was to stick these two together, 45 plus 45 is 90 degrees. So I would have 90 degrees here and 90 degrees there. Ooh, didn't we just do a theorem about this? If two lines are perpendicular to the same line, then those two lines are parallel. I think we did. Alright, so take a look at this. Can you assemble the pieces here to form a picture frame with opposite sides parallel? So, can we do it? Well, if we were to line up these two corners, we would have a 30-degree angle plus a 60-degree angle. That would be 90 degrees. And then if we take this point here and put it up there, we'd have a 30-degree angle plus a 60-degree angle. That's a 90-degree angle. And we'd have the same thing at the bottom. So yeah, same theorem we're using. We'll have two lines perpendicular to the same line, so these two would be parallel. And then the same thing would apply to these guys here. Ooh, a perpendicular transversal theorem. In a plane, if a line is perpendicular to one of two parallel lines, then it is also perpendicular to the other. So this one's kind of it's almost like the converse of the last theorem we did. If N is perpendicular to L, and L is parallel to M, then N is also perpendicular to M. So the perpendicular transversal theorem states that the lines must be in a plane. In a plane. And this here diagram shows you why. So you'll notice that line AC is parallel to line BD, and that line EC is perpendicular to AC. But EC is not perpendicular to BD because they're not in the same plane. They're actually skew. Right? To be perpendicular, you have to be in the same plane. So BD and CE are skew. Skew lines. Skew. And your secret code phrase is whoppers. Whoppers. Alright, let's prove a relationship between two lines, shall we? Shall we? In a plane, C is perpendicular to B, and B is perpendicular to D, and D is perpendicular to A. Prove that C is perpendicular to A. Now, good thing we said in a plane. All these are in a plane, so we can use our theorem. So let's see, how shall we start? Lines C and D are both perpendicular to B. So that means that C is parallel to D. Because of the theorem we just had, two lines perpendicular to the same line are parallel. Okay, so now we got two parallel lines here. And then we got a perpendicular line that's A is perpendicular to one of them. It's given that D is perpendicular to A. Therefore, C is perpendicular to A by the perpendicular transversal theorem. That if a line is perpendicular to one of two parallel lines, then it is perpendicular to both of them. So we just proved that C is perpendicular to A. So in problem 2, could you also conclude that A is parallel to B? Can you conclude that line A is parallel to line B? Well, I'll tell you what, the answer is yes. Because we have one line that is perpendicular to both A and B. And that is basically theorem 3.9. If two lines are perpendicular to the same line, then they are parallel to each other. Yes. Theorem 3.9. Hey, we're done. That's pretty cool, right? You're welcome.